I want to continue on the concept of impulse that we looked at in this chapter. All right, so we use capital J for impulse, and I'm writing this as the average collision force, okay, multiplied by the time over which that collision force occurred, okay. And the weird thing about the concept of impulse, if there's a collision force and that collision force occurs over a period of time, and usually it means a short period of time, okay, we actually have two different words for this quantity. We could either call it the impulse, okay, which refers to the force that that acted on an object over this short period of time, and we also refer to it as the change in momentum of the object. Okay, so there's two different ways to look at a force acting over a short period of time. Okay, we use the example of the baseball hitting the bat. Either talk about how the baseball changed momentum, or we talked about how the bat exerted a force over a short period of time to cause that change in momentum. Okay, so even though this is in our current chapter, I claim that you knew all about this stuff back in third grade. All right, so here's a person, and what is this thingy? Okay, so these are two straws taped together to make a double barrel spitball gun. Okay, so here's top straw is number one, bottom of straw is number two. Okay, and the person's blowing on it, so both straws have the same force, okay, of air. All right, so you knew back in third grade where to put the spitball wad. Did you put it over here? I call that number one. Or did you put it over here at the end, number two? Okay, so you knew to put it at place number one. Okay, and the reason you knew that is this concept of impulse. Okay, so the idea is both of these spitballs are going to have the same force. They have the same force acting on them. But spitball number one is going to have that force acted upon. I'm over here. Spitball number one is going to have that force acted on it for a much longer period of time because it's going to travel through the whole straw. Okay, so it's going to get a large change of momentum. Okay, remember, momentum is mass times velocity. Well, the mass of the spitballs is the same. But if you have a large change of momentum, that means number one comes out with a huge speed. Okay, spitball number two, all right, has the same force on it because both the straws are in your mouth, has the same force. But since it's only traveling a little distance because it's almost near the exit hole of the straw, the time over which that force acts is really small. So it gets a very small change of momentum, meaning it exits with a small speed. So that's the picture I have here. So the idea is you knew to put the spitball here because you want it to maximize the time over which that force acted. You want to maximize the impulse. Right? So that's why I show spitball number one goes all the way, right? You can even sit in the back row and hit the teacher in the front. Okay? Whereas spitball number two, right? You couldn't even hit the teacher from the front row. Okay, now, a similar idea is making a balloon rocket. And I'm going to show you a video on this in a second.
The balloon shoots forward just like a rocket.
So essentially what this is, I have a balloon. Okay, the balloon is blown up, so the little dots are the air. And then a person is holding this here. So they're holding the balloon so the air stays in it. And then you can actually tape a straw. There's a straw. You can actually tape a straw to the balloon. Okay. And then here's a string. Okay, so you have the string going through the straw. And then when you let go, okay, so the person lets go. This is the after picture. Person lets go. The air flows out of the balloon. Okay, air flows out to the left, and the balloon recoils or moves off to the right. So here's my before picture. Before picture is just you're holding on to the balloon, okay, or even if the balloon is taped shut. Okay, initial momentum is zero. The balloon's just sitting there. Okay, remember momentum, mass times velocity. Okay, so balloon's not moving, velocity zero, momentum zero. The final picture, in the after picture, you have the momentum of the air that comes out of the balloon, okay, and you have the final momentum of the balloon. So if I solve this for the final momentum of the air, that says that P final for this air is equal to minus the momentum of the balloon. So they're equal and opposite. So the balloon moves off to the right, the air moves off to the left. And so you saw in the video that the balloon actually accelerates off to the right. So this idea is the exact same of how a rocket works, and also the example we did of an astronaut's jetpack. So here is the jetpack, and this balloon is emitting the exact same thing that the jetpack does. Okay, so the jetpack, it might not emit air, but it still emits a gas. It emits mass. So anytime you have a bunch of mass sitting there, and now all of a sudden some of that mass starts to head to the left, the rest of that mass has to head to the right to conserve momentum. Okay, now in the early 1900s, about probably more than 100 years ago, there's a person named Robert Goddard, and he's considered the father of modern rocketry. Most people credit that to Elton John, but it's actually Robert Goddard, father of modern rocketry. So he was doing experiments with rockets and had the idea that you could have something propelling a rocket through space. So in 1920, okay, the New York Times, they published an editorial pretty much mocking his idea that you could have a rocket work in space. And so they said that that could never work because he doesn't understand you need to have an action reaction, that just like our balloon pushing out air, they thought you had to be able to push on something and have that something push back. Okay, so they kind of mocked him back in the 20s that would never work, right? And actually, okay, that was in the 20s, and actually he was finally vindicated in the 40s, okay, when the Germans launched this missile, and then obviously later in the 50s when Sputnik went up, was the first satellite. So they mocked him in the New York Times in 1920, and then it wasn't until 1969, okay, why'd they wait till then? Because that was the day after people set off to go walk on the moon. Okay, so this is the retraction that they printed in 1969, which is what, 49 years later. They said the Times regrets the error.